So share my screen again. And all right, so yeah, be able to calculate a code word for a linear block code given an input message and a generator matrix or parity equations, right? So maybe we know that generator matrix is composed of an identity matrix plus a series of columns that each represent a parity equation, right? And we have a one in a particular row of a column that maps to the input bits, right? And then we use modulo 2 addition, and we might have a set of parity equations, right? So depending upon the size and the code rate of the code. So just be aware that yes, we use modulo 2 addition, and you're multiplying the input bits or message vector by the generator matrix, right? And so the vector goes on the left, the generator matrix goes on the right. We also, in the previous exam, we decoded a linear block code using syndromes, and some did great on this, and some had some problems on that. So basically, I'm giving those that had problems with it a chance to really learn this and demonstrate that they know it now, right? So that's why these things are showing up again on the exam. So there we take our received vector, which we normally indicate by an R, a lowercase r. So we are going to receive some code word, may or may not have errors in it, right? And we multiply that code word times h of t. You can conceivably generate an h of t given a generator matrix, right? You could find the h of t from the generator matrix, right? But you may be given the h of t, so you're multiplying r times that h of t. That produces a syndrome, right? And that syndrome, in the previous cases, it was 3 bits long, right? And that's again a consequence of the size of the code rate, that type of thing, right? And then each of those codes, each of those syndromes is going to correspond to a particular error vector, right? The error vector is going to indicate the most likely bit position of an error, right? It's not absolute, it's just the most likely place, right? So the most likely error is that you had 1 bit error out of your code word, right? So if our code word is 7 bits long, then and we have input bits of 4, our overall code word is 7, and therefore we have 3 parity bits, right? So the most likely situation is that there's just 1 bit that's in error. So our syndromes correspond to a single bit error vector, right? So that error vector is 7 digits long. It has 6 zeros and 1 1, right? Somewhere, right? And or there may be no errors, right? So that error vector signifies the position of the error, the most likely error bit. And if we add that to our received error vector using modulo 2 addition, which as a review is the same as a bitwise exclusive OR operation, right? But a modulo 2 operation, we add the R plus the error vector that produces our code word, our most likely sent code word. Then for systematic code, we know that the first few bits, in the case of a 4 input bits, those first 4 input bits would be directly from your code word, right? So you could, if your code word is 7 bits long, and your generator matrix is starting with the identity matrix and then follows with the parity bits, which is just by convention how we've taught it. It's not absolutely ordered that way, but that's how we've talked about it. Then those first 4 bits would be the most likely input message, right? So your input message that was sent should be the first part of that code word, right? So then we also calculate the path metrics at a certain stage in a trellis given a set of received bits, right? So we here I think we can come on switch. Oh, that's homework. Where's my exam? Okay, so like, for example, this problem here we had on the previous exam, right? And in this case, I was generous and gave you the path metrics up to this point, right? But really, given the structure of the trellis, right, that your convolutional code is going to produce certain legal transitions, right? And then you have received bits, then you ought to be able to calculate the metrics here, here, and here, right? So again, as a review, you would compare these second 2 bits, or the bits after the diagonal slash there, to the receive bits and add those up. All right. So we've got we received a 1-1 in this case, and but the legal expected for this transition was a 0-0. So that's different in 2 places. So we sum up the number of places that it was an error, and that's a 2. So we would write a 2 right there. And then we got 1-1 and 1-1. Oh, those are the same. So it'd be a 0 right there. And then we look at the next step, right? And now this, we can calculate branch metric, but then add it to the path metric, right? So here we've got 1-1 and 0-0. That's another metric of 2. We add that to the previous 2, and we end up with 4, right? And here we've got 1-1. Well, that matches that 1-1. So this branch metric here is 0, but when we add it to what's already accumulated error, that's 2. So 2 plus 0 is 2, and so on. Then when we get to this stage, now we notice that each node has 2 potential paths coming into it, right? So over here, we assume that we start the decoding process with in a state of 0-0, right? So we're not accounting for transitioning from any of these other states, right? So it's not until we get to this location here where to arrive at this state, we could have gotten here from 2 different directions, right? And so our job is to try to predict what is the most likeliest direction that we came from, right? So again, we calculate out the metrics, but now for this node here, we need to calculate the metric from this path, this transition, and also this transition. Now, since our paths are, these metrics are really recording or summing up the number of times that there was an error or a mismatch between what we got and what we expected for that path, then you can easily remember that we really want the smallest, right? We want these smallest metrics here. And because that would reflect the fewest number of errors to get to this point, right? So here we've got a 0, 0 compared to a 1, 0. So there's a difference of 1 there, but we got to account for all the errors that we've accumulated to get to that point already. So that's 4 plus 1. So that'd be 5. So we might write, 5 out here as a note. And then we look at how else can we get there? Well, we can get there from this direction, right? And we got a 1, 0 and a 1, 0. Okay, so that's, am I reading that right? Oh, I'm sorry, it's a 1, 1 right here. All right, so it's a 1, 0 versus a 1, 1. So that's a difference of 1 plus this existing 1, that's 2. We compare the 2 versus the 5. We choose a smaller one and we record that. We put 2 in there. And then we cross out the path that had the higher metric. We're going to ignore that one from now on. And we're only going to retain the one that has the lower metric, right? Because lower is better. It's like golf, right? So, all right, except when I play golf. Okay, so that's a reminder of how to do that. And so that was exam 1. Where's my exam? Okay, so encode the source bits efficiently using one of the source encoding methods we studied, Huffman or Lempel-Ziv, and we've studied both of those. There's plenty of others, but those are the ones that we've studied. Now, if we go back to like exam 3 here, we remember that the Huffman requires you to know the probabilities a priori, right, beforehand. You've got to know these probabilities. But if you do, then you can kind of draw this graph out in such a way that you can encode these symbols using the minimum number of bits, right? And that tends to favor the bits, the alphabet letters that are most likely to occur, right? So since X1 here is far more likely to occur than any of the others, it's most efficient to just encode that with the value of 0, and the others, well, we encode those with values of 3, right? Three digits, which seems a little wasteful, but these are so low in probability that we're rarely going to need those 3 bits to encode those, right? So we do that by building up this little tree graph here. We always combine the lowest probability ones, right? So here we combine 0, 5 and 0, 1 to get 1, 5. And then we look and say, okay, well, actually 0.12 and 0.13 are the next lowest probability ones. So we combine those. Then we combine the 0.15 and the 0.25 because those are the lowest probabilities, right? These are joint probabilities now, right? And then we end up with 0.4 and 0.6 combined. And then we label these paths in this tree with zeros on the top and ones on the bottom, and we just follow it, right? So it'd be 0 to get to there, but to get to this 0.13, we go to 1 and then 0 and 0 to get there, right? Or to get to the 0.1 letter, we go from 1 to 0, right? So the Lempel-Ziv algorithm here, recall that we are trying to find unique phrases. And so we just start. Now we don't need to know the probabilities a priori. We build this up on the fly as we go, right? And so we write down the unique ones. Well, that first one is unique. We write that down. And then that next one, okay, one's not unique, but 10 is, right? And we write that down. And then the next one is 0. We write that down. And we keep parsing this into unique uh, phrases, right? And so then we record those. Then to generate our code words, we if we just have one digit here, then we're going to use an address of 000, right? So we have the first part of the code word, the left part of the code word is going to be the address of the previous digits. Well, this has no previous digits. It just has one digit. So it's 000. And then we record those digits, which or the digit on the right that made this phrase unique, right? And but here, when we do this 10, when we try to write that code word, we look at the one, the preceding part of the code word of this phrase. And that's one. We find that in our table, and that's at an address of 001. So we write down 001, and then the bit that made it unique, right? Which is at 0. Then we do the 0. Well, again, that's just single digit. So the part that made it unique was just it. And so there was nothing to refer back to. So we write down 000 and then that 0 as unique. Continuing on, we do this 11. Well, the 1 we find there, 001, and then the part that's unique, 1. 00, we find that 0 back here, 011. We write that down, and then plus the part that makes it unique. 101, we find a 10, that's here, 010, and we write down what makes it unique. Okay, so those are the two source coding algorithms that we study. Okay, so then also understand why and when we might want to use spread spectrum waveforms, right? So the main thing is to overcome narrow band jammers or interference, that type of thing, right? So if we are using just enough bandwidth to communicate, based upon Shannon's capacity theorem, says we need a certain amount of bandwidth given a certain signal noise ratio. And if we just use that bandwidth, and then someone comes along and either intentionally or unintentionally transmits on top of us, then it wipes out our whole signal, right? And but if we and we have no margin left to recover anything, right? Because Shannon says we need a certain amount of bandwidth, and someone's interfering over a significant part of that bandwidth, then we're not going to be able to achieve our goals, our communication goals. But if we spread that, and we talked about using frequency hopping to either slowly or quickly hop from one frequency to another, then it makes it harder for a narrowband signal to interfere with us, right? So in slow hopping, we might send a whole symbol or a few symbols at a time and at a particular channel. And then if someone's jamming that one, then we end up, we might lose those bits, but or those symbols. We might not be able to estimate those correctly. But if we've used some error control coding, we'll be able to hopefully be successful when we hop to another channel and find the redundant information there, right? Or if we're using fast hopping, now we're hopping to more than one channel for a given symbol, right? So we're trying to send a symbol, but we're hopping really fast. And now we're, if we have a narrowband jammer, then we just lose a little bit of that signal energy, right? And or it messes with our estimated signal energy a little bit, but only when the frequency hop and that jammer are at the same time. Oh, gosh, Bitdefender is driving me crazy here. Sorry. So if we then we're fast hopping, then we'll be at other frequencies really momentarily, and those won't be jammed, and we'll be able to recover that information. So that's the main thing about spread spectrum. That again, that could be someone jamming us intentionally, or it just might be that, like in the case of Bluetooth, hey, a bunch of us all want to talk on the same overall frequency all at the same time, and we're all, doing our own thing. There's not a centralized base station that's controlling it. We are just hopping according to our own wants and desires, right? So there's a chance that we'll, let's say there's two of us, we'll both hop onto the same channel at the same time, and yeah, we'll have a collision. We won't be able to detect that symbol correctly, but then we'll hop away. And assuming that we're not using the exact same hopping sequence, then we'll be able to recover our signals later on, right? So, all right. Understand MIMO. So we talked about single input, multiple output, multiple input, single output, multiple input, multiple output, right? And let's see, do I have yeah, and then like I talked about this Alamudi as being one type of, or a kind of a classic type of MIMO type situation. And that's when we we have two antennas, and on during a given symbol period, we'll send two symbols, right? So symbol one, symbol two. So normally we would send those in sequence. We'd send symbol one and then symbol two. But if we have two antennas, we actually send them both at the same time. We send symbol one on one antenna, symbol two on another antenna. But then in the next symbol period, we kind of mess with them a little bit. We flip them around, and we send symbol two on antenna one, but we take the complex conjugate of it. And then we take symbol one and send it on antenna two, but take the complex conjugate and then multiply it by a -1, right? So we're sending basically the same information, but a little bit modified. As it turns out, when you multiply this through now, we can actually get a gain in doing that, right? So because we know that this has been done using a certain structure, right? Certain pattern. And so we can count on that. So now this is going to be that Frobenius norm. I'm probably horribly mispronouncing that. I got to see it to be able to pronounce it. But this is where you take all the individual elements and square them and then sum them up. And so kind of like a Pythagorean theorem type of thing, right? So very, very loosely speaking. And so we get a little bit of a gain here. Yeah, we're multiplying our noise by this H matrix also, but we're multiplying our signal by a lot. So that's done using this kind of specialized pattern here that's reflected in our H matrix, right? And so this is our channel response matrix. And so if we multiply our Hermitian of that by our received symbols, then Z is our estimated result. It's going to be a vector, and it'll scale the value of S's, so we'll be able to recover those S's pretty well, right? So other things about MIMO that we've talked about. So if we want to use like pre-coding at the transmitter to so where we would have two antennas here, then we're pre-coding it so that basically when these two different signal rays arrive at the receiver, that they're already going to combine constructively, right? So we've kind of pre-coded or pre-messed with these signals to compensate for the fact that this channel is a little different from this propagation channel, right? So that then when both of these electromagnetic waves induce currents in this receive antenna, that they're already constructively adding, right? And but that requires us to have this knowledge of these channels. So we call that channel state information, or CSI. So we need to know the characteristics of these channels here, right? The amplitude and phase, basically, of that channel. So we estimate that at the receiver, and we feed that information back to the transmitter. There's some subtleties here in that in typical cell phone systems, we use a slightly different frequency for our downlink than we use for our uplink, right? So that means that the receiver and your channels are going to be different then, right? You change your frequency by just a little bit, and all these channels characteristics change a lot. So the receiver characterizes these channels based upon these kind of sounding symbols. So we encode our waveform certain slots, frequencies, and time of known symbols, right? Have certain amplitude and certain phase, and we know that that's what's supposed to be sent at that particular time. So the receiver looks at those, measures them, measures the amplitude and phase, compares it to what's sent here, right? So we like at one instant we'd send the training symbol or reference signal for this antenna, and then maybe a few instants later we'd send this one, right? And typically we're only sending one at a time, and so the receiver can measure that ray right there at that instant, and then in, let's say, the next instant or the next known location of these known reference signals, it will measure that one. Now it has that information. It encodes that information, sends it back to the transmitter. Now the transmitter can use it in this linear pre-coding. And of course, then the receiver moves and it's got to be done all over again, right? So it's a continual process. That's in comparison to the SIMO situation, where here all that linear combining is done at the receiver and stuff. So But when we do that, we're also affecting the noise. So we did some math on that, but we know that if we can pre-code it, then our noise doesn't get amplified, whereas it does get amplified a little bit in this situation. Now, in some cases, in a few cases, we use time division multiplexing, and our downlink and our uplink are done at the same frequency, just at a little different time. Okay, so we'll do a downlink, and then we'll turn around and do an uplink. And in that case, we can assume that this channel is reciprocal. It's that same frequency now, right? And so the channel's reciprocal. So we can estimate the channel at the transmitter by looking at the receiver signal, right? And then we don't have to like measure it here and then send it there. We can assume that the channel this direction is reciprocal to the channel that direction. But that's rare. Most implementations use two different frequencies for the downlink and the uplink. And so that means the channel is not reciprocal, that the channel this direction looks very different from the channel that direction. So to properly pre-code the channel, the signal going in this direction, we've got to measure it at the receiver. Okay. So also we talked about how it's important in MIMO to have some multipath. If we don't have kind of a rich multipath environment, then we're not really able to do this pre-coding or linear combining in an effective way. That even if we can, like typically there's the equivalent of a matrix inversion, and if everything's too similar, then we'll end up in a singularity type situation, a singular matrix, and we won't be able to invert it, or it won't be numerically stable in doing so. Even if it's not that bad, we will, when we do that, our numerical ability to like measure this channel and then invert it, that it will be kind of the noise or the inaccuracies, numerical precision loss in doing that operation is going to dominate over any of the differences that we actually get. So we actually want a rich multipath environment here, right, for MIMO to work. If we have, when we talked about a little bit about Rayleigh fading versus Riccian fading, and the distinction was that Rayleigh fading has a strong line of sight component where one of these rays will be much larger than the others. MIMO is not going to be quite as effective in that situation. If you only have one ray, it's not going to be effective at all, right? So if all these things are too close to the same. So it's essential that you have a rich multipath environment. All right, let's try to wrap up here. Understand the basic concepts of orthogonal frequency domain multiplexing. Here we're trying to send multiple narrowband carriers and try to see how close we can squeeze those together, right? And again, that's where we end up with that sin x over x frequency dependency now. And we squeeze them together in that orthogonal condition where the nulls of that sync x response lay on the peaks of the others, right? Or vice versa. And that is our orthogonality condition. When we went through the math on that, we recognized that, boy, that looks just like an inverse Fourier transform. So that's how we generate it. We use our efficient fast Fourier algorithms to do an IFFT and combine all of our subcarriers, our narrowband subcarriers, into one. Those narrowband subcarriers, I'm sorry, I'm running out of time here. So each of those narrowband subcarriers can be modulated at a different depth or level, maybe 16 QAM versus BPSK versus 64 QAM, depending upon the signal noise ratio you experience in that particular region. Know what a cyclic prefix is and why we use it. Know the 5G use cases. That's a kind of enhanced high bandwidth type of situation, the ultra low latency, high reliability use case, and the kind of massive IoT type use case. They're listed in that PowerPoint. Understand the basic concepts of cellular communication. The big thing here is we're dividing up that spatial dimension. Instead of trying to blast our signal as loud and as far as we can and cover a huge region, we actually purposely try to scale things down and only communicate over a smaller region. And that way then we can add multiple cells, and each of those will be somewhat independent and be able to support their own set of users. And we're actually able to divvy up space in a way that we can support more users. And then finally understand that standards process, be able to name a few standards organizations that are active in wireless communications, and be able to talk through that IEEE standards process, the ones part of that I emphasized in the presentation. So this is up on Moodle, so please take a look at it. And yeah, it looks like I'm out of time. So I'll be available on Monday. If you have questions, it's best to shoot me an email. And I can possibly be available at other times, but yeah, shoot me an email and set something up if you need some help there. So okay, good luck. Take care.
Have a good one.
Have a great summer.